Anytime you're dealing with biochemistry, it's important to understand the shape of molecules. And when we talk about shapes in molecules, we have to talk about isomers. So we're going to do a few things in this video. We're going to look at what an isomer is. We're going to look at why they matter. And we're finally going to look at the three major types of isomers. So let's start by defining what an isomer is. An isomer is basically a molecule, or excuse me, it's actually two molecules would be isomers that each have the same molecular formula, but they're going to have different shapes. So they're going to have the same molecular formula, and if you recall, the molecular formula just simply means the actual elements that that molecule is composed of. They'll have the same elements and the same number of elements, but their structure is going to be a little different. So one thing you may wonder is, why does that matter? The number one factor in determining what any biological compound does is going to be its shape. So when we think about proteins and we think about enzymes specifically, we talk about how they fit like a lock and key. And so if an enzyme and a substrate don't exactly fit with one another, then they're not going to be able to react. And it is the shape of the enzyme and the substrate that causes that relationship. And so if you change the shape of a molecule, you're going to change a little bit about what it does. So let's talk about the three major types of isomers that we experience in biology. The first type we're going to look at is what we call a structural isomer. And these types of isomers are just going to differ in the location of their functional groups. The second type that we'll look at is what we call a geometric isomer, or sometimes it's called a cis-trans isomer, and they are going to change in regard to their geometric shape around a double bond. And the third type is what we call enantiomers, and they're going to be kind of like molecules that are like mirror images of one another, kind of like your hand. So you have a left hand and you have a right hand, and your left hand and right hand have the same components. They have the same fingers, four fingers and thumb, and they're all relatively the same size, but unfortunately your left hand won't fit in a right hand glove and vice versa, and so they are different. So let's look now at our first type of isomer, structural isomers. And we said that those are isomers that have the same molecular formula, but they're going to have different physical structure or different shape. So here we have a good example. This top molecule we have is called isobutane, and it's named butane because the BU, the butane, means that it has 4 carbons, and this bottom molecule is just what we call butane. Now, both of these are going to have the exact same molecular formula. They both have 4 carbons, so C4, and they both have 10 hydrogens, so H10. But as you can see by looking at them, they have different physical structure, so we're going to actually draw that out. Isobutane is made up of a 3-carbon chain, and I just put these dashes here to represent hydrogens. It's just understood that those are hydrogens, but it's going to have another carbon, like a methyl group, attached to the top. So again, we have 1, 2, 3, 4 carbons, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So we have this molecular formula C4H10. If we draw out butane, it has a different shape. It's actually made up of 4 carbons, a 4-carbon chain, and I'm going to draw in the hydrogens. And if we count again, we've got 1, 2, 3, 4 carbons, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So they both have the exact same molecular formula, but they have a different structure, and that is a structural isomer. The next type of isomer that we're going to look at is geometric isomers, and these are going to be molecules that differ around a double bond. This is actually going to be a difference in symmetry. Again, they're going to have the same molecular formula. We also said that another term for geometric isomers is cis and trans isomers, and we're going to find out why that is. If we look at these two molecules here, before we go over the name of them, this down here at the bottom is what we call the cis isomer because it has the same functional groups on the same side of the double bond. So here's our double bond, and this functional group exists, both of them exist on the same side. Trans, another word for trans is across. So in a trans isomer, here's our double bond, and the functional group is on either side, or they're across from one another, across that double bond. So we would call this on the bottom the cis isomer, and this at the top we would call the trans. So the one on top we're going to call transdiazine, and the molecule on the bottom will be called cisdiazine. Now this double bond that exists in between these two nitrogens, because basically what we have here is we have two nitrogens that are double bonded to one another, and those are each connected to a hydrogen. So in the trans formation, those hydrogens are across from one another. In the cis formation, they are both on the same side. And the reason for this scenario is this double bond. The double bond does not allow the molecule to rotate. Normally, if this were just a single bond between them, and we had a hydrogen on one side and a hydrogen on other, the hydrogens could swap back and forth to either side, and sometimes we'd have a cis scenario and sometimes a trans. But because that double bond keeps the two molecules from rotating around one another, the molecule is either going to exist in the trans state or it's going to exist in the cis state. The last type of isomer that we're going to look at is probably the trickiest one in enantiomers. And a few things we can remember about them is they are going to be mirror images of one another. So just like when you look at yourself in the mirror, you're seeing yourself, but you're really seeing the exact opposite of yourself. Sometimes we say that they are kind of like human hands, because you can put your hands together like this, and they are exact mirror images of each other. If you drew a line down the middle, you would have exactly on one side what you have on the other. So at the surface, it seems like they're exactly identical, but the reality is if you tried to put a left hand in a right-handed glove, it would not fit, and vice versa. And so you really have a left-hand configuration and a right-hand configuration, and even though they have the same exact components, they're really different from one another. So here we have a perfect example of two enantiomers. I like this picture because it's actually showing a person's hand. So we have a right hand configuration and we have a left hand configuration. And you'll notice as you look at these two molecules, we have the same exact molecular formula. We could count up the number of carbons. We could see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons in this molecule, and over here there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in that one. We could count up, see here's oxygens, they each have one oxygen. We could count up the number of hydrogens if we wanted to. And unlike structural isomers, they seem to have functional groups, like this oxygen, in the exact same place, but the reality is they are different. They are mirror images of one another if we put a mirror right down the middle. And so therefore they do have different shapes. And the main thing about biological molecules is if something has a different shape, that means it's going to have a different function. So very quickly, let's review. We talked about isomers. And isomers are simply molecules that have the same molecular formula, but they're going to have different shapes. So in other words, they have the same elements and they have the same numbers of each element, but they have different shapes. We talked about why that matters, and the reason it matters is because biological molecules, the shape is what determines the function. So if we have two molecules with different shapes, even though they have the same formula, they're going to have different functions. And then we talked about the three types. The first type was structural isomers, and those are isomers that have the same formula but have a different physical shape. And that was like isobutane and butane. The second type that we talked about was geometric or cis-trans isomers. And geometric isomers were like the diazine molecules we had when the functional groups are on the same side, like so, we call that the cis, and when they're on the opposite side, we call that the trans. And remember, geometric isomers are asymmetrically different around a double bond. And finally, the third type we talked about was enantiomers. And if you recall, those are molecules that have the same formula and basically the same structure. They are just mirror images of one another, kind of like our hands. And these are the three major types of isomers.